Okay, welcome to today's topic. We have already discussed series circuits. Today we're going to discuss the second type of circuit we'll talk about, that is parallel circuits. We know that the defining feature of a series circuit is that they only have one path for the current to flow around. The charges have to move in all the same, they have to move the exact same way through the circuit. There's not alternate paths. Well, then fairly obviously, parallel circuits must be, well, different from that. Parallel circuits have multiple paths through which current can flow. So let me draw you two different examples of a parallel circuit. You might see a parallel circuit that looks something like this. Where you have a branch in the circuit right here. You have some resistors. And then the circuit loops back around, in which case you can clearly tell that there's two paths for the circuit, for the current to flow through. It could flow from the battery through this wire through the upper resistor and then back to the other side of the battery, or it could flow through the lower resistor. Okay, you won't have any current that goes through this resistor and then goes through the other. Charges won't flow back the way they came or flow against the flow of other charges. All the charges are going to be moving in the same direction. It's just that the current will split at certain points. So we have two different paths that the current could flow through. We could also have something that looks like this. This is how I typically draw circuits, by the way. That's just what I grew up drawing. You could also have a parallel circuit that looks like this. Right now it's just a series circuit, but if I do this, we've now made it a parallel circuit. And you can do this for however many resistors you have. So this is a parallel circuit with two resistors in it. This is a parallel circuit with 3 resistors in it. And let's see, here we have 2 separate branches, here we have 3 separate branches. Just to show you that you can draw these on the computer, here are some examples. Here's that first kind that we talked about. Notice that you have the current splitting at this junction right here. Okay, and then recombining at this junction right here. Okay. And we have another circuit. Here's another example. We have two places where the current splits, here and here. And then we have 2 places where the current recombines, here and here. Different examples of different examples of parallel circuits. Okay. So, parallel circuits with resistors in them, they still follow Ohm's law, but there are different rules. Okay, remember Ohm's law is V equals IR. That was the same as for series circuits. V equals IR was kind of the guiding principle as we worked our way around series circuits. But the rules for series and parallel circuits are different. Okay. So what we're going to do now is we're going to go over the rules for series and parallel circuits. So for a simple parallel circuit with 1 resistor per branch, and that's really the only type that we're going to be studying, the voltage drop for each resistor is the same. Now contrast this to what you knew about series circuits. With series circuits, the voltage drop depended on how big the resistance was. Here, with parallel circuits, we have something different. The voltage drop for each resistor is the same. So what I'm going to do is I'm going to draw you 2 pictures. One is going to be wrong and one is going to be right. I'm going to start the pictures off exactly the same. Let's say we have a 6-volt battery that has 2 resistors in parallel. Like that. And we have a voltmeter attached across both of these. Okay? So that voltmeter is reading essentially the voltage drop for these resistors. me draw the same thing over. So this is the wrong side. This is the right side. Okay. So, on the wrong side, the wrong assumption to make would be to say that we have something like a drop of 4 volts for this resistor and 2 volts for this resistor. That's series circuit logic. You might say, well, 4 plus 2 equals 6, so the total voltage drop has got to be 6. No, that's not true. Okay? That is not how parallel circuits work. In fact, how they do work is this drop will be 6, and this drop will be 6. Notice, I'm not saying anything about the size of the resistors. I'm just saying the voltage drops will both be equal to the voltage drop from the battery for a parallel circuit. Let me show you that this is indeed the case. We go over here to our setup. We know it's a 6-volt battery. Let's look at the voltage drop from both of these resistors. 6-volt battery. That's a 6-volt voltage, a 6-volt drop, and so is this. Okay, so that's proof of what we've been saying. The voltage drops for resistors in a simple parallel circuit like this must be the same as the voltage drop of the battery. Okay, so the drops. This is the wrong side, by the way. Add to 6 volts. But the reason this is wrong is then the charges would have contradictory energies. In other words, it wouldn't make sense. If you said that there was a 6-volt potential difference between the different sides of the battery, and that charges that went through this left branch had a voltage drop of 4 volts, that means that they still have a 2-volt difference between here and here. Charges that went through this right branch would have a drop of 2 volts. They would have a difference of 4 volts between when they recombine and they get back. That wouldn't make sense. You can't have some charges going through that are carrying more energy than others, and they're the same size. That doesn't make sense. Okay. And in addition, there's no other place for them to drop that energy from here to here. So then the whole idea that this was 6 volts in the first place would be wrong. Okay? You can't have, anywhere on a circuit, if you were to evaluate the voltage, no matter what path you take through the circuit, you should get the same thing. Okay? So you can't say that the charges have dropped 4 volts by this point if they went through the right path, and only 2 volts by this point if they went through the left path. That's not how it works in a very simple parallel circuit like this. On the other hand, here, just ruin my paper. Each drop is equal to the total voltage of the battery, which makes sense if you think about it in the light of conservation of energy. With conservation of energy, you have a situation where if there's a 6-volt difference with the battery, as the charges go through the circuit, there better be a 6-volt difference with some sort of power consumer, some sort of energy consumer. So as the charges go through the battery, they gain 6 volts of energy. As they pass through the resistors, they give up that 6 volts. Okay, remember, circuits are just a way for us to efficiently get energy from point A to point B. Okay, so that's rule number 1. The voltage drops for resistors in a simple parallel circuit are the same. Rule number 2. Each branch of a parallel circuit can have a different current. Doesn't mean they have to have different currents, but they can. The sum of the currents in each branch of the circuit is equal to the total current flowing out of the battery. And the higher the resistance in a branch, the lower the current in that branch. Again, I'm going to draw you a right and a wrong. So this will be our wrong. This will be our right. Remember what that A means. A is the symbol for ammeter. Okay. So, it would be wrong of us to say that the current in this ammeter is 4 amps. Let me apply some series circuit logic to this. If you knew a lot about series circuits, but not a lot about parallel circuits, you'd say, well, there's got to be a 4 amp current heading this way, and then, oh, here's a junction, so the current will split. We have 4 amps coming down this way, and 4 amps coming this way. Do you see the problem with that? The problem with that is you've just created 4 amps of current. You had 4 amps here. Now, suddenly in the branches, you have a total of 8 amps. 4 amps here, 4 amps here. The reason that doesn't work is because, remember, current is simply counting how many charges are flowing past a point per second. You can't have 4 amps here. Okay, that means a certain amount of charge flowing past a point in a second here, and then just magically more charges appear, and they flow and go through this section of the circuit. It doesn't work like that. Okay, you can't just magically create or destroy charge. There's a rule called conservation of charge. So, anyways, the reason this doesn't work, the current out of the battery is 4 amps. And here, in this picture, the current, well, the total in the branches is 8 amps. Just remember, the current can't magically increase. Okay? Here's how we would correctly analyze that. If we indeed had 4 amps flowing out here, if this ammeter said that there was 3 amps here, we would know that in this branch, there must be only 1 amp. In other words, the branch currents add to equal the total current out of the battery. Okay? Let me show you that this is in fact true. Let's go back here. Okay, let's get out the cheating ammeter. So we'll bring this over. Let's look at the current out of the battery, 0.9 amps. Let's remember that. Now, in a series circuit, we would expect all the currents to be equal. But that's clearly not the case. This is 0.30 amps. Now, if we do some math, you can probably guess what this must be. 0.60 amps. And matter of fact, if we add 0.6 and 0.3, we end up with 0.9. So not only are the voltage rules different for parallel circuits, the current rules are different as well. And this leads into rule number 3, which is kind of what we just talked about. The amount of current that flows into a certain junction, where wires either split or come together, must equal the current flowing out of the junction. This is just a restatement of conservation of charge. So, let me give you an example. Here's a junction. We have some wires flowing with current flowing into the junction. Let's say this is 6 amps and this is 5 amps. We have some wires that are carrying current out of the junction. If this wire is carrying 7 amps out, how much current is flowing out of this wire? Well, this isn't really an equation per se, but you could write something down that looks like this. Current in equals current out. The total current in is 6 amps plus 5 amps. And the current out is 7 amps plus question mark. you can all solve that algebra to say that, oh, this is 11 amps total going in. So it must be 11 amps going out. 7 plus what gives us 11? The question mark is 4 amps. Okay. And again, we can demonstrate that on the computer using the simulation. Now this is I'm gonna have to zoom in a little bit for this one. Okay. So I built a circuit here that shows the current at different points. And it's an exact replica of what we just did. We have a current of 5 amps flowing in here, 6 amps flowing up from the bottom. We have 2 wires carrying current out, so that's a total of 11. If this wire has a current of 7 amps flowing out, this one we said must have 4. What do you know? It does. When you come back, we'll talk about equivalent resistance for a parallel circuit. We'll see where all this stuff is referenced in the reference tables, and then we'll do some example problems.